Hey guys, Mr. Betts here. Now that we've got some calculus tools at our disposal, we're going to be able to start using them to apply it to real life situations, or at least realistic situations. And one of those types of problems that we're going to apply calculus to is called optimization. So, optimization is exactly what it sounds like. Essentially, what we want to do is figure out how to make something as big as possible or something as small as possible, depending on what we're looking for. So, for example, if we're like modeling profit for a company, we're going to try to make that as big as possible. On the other hand, if we're modeling how much material we're going to use to make a certain product, we're going to try to minimize that. So, depending on the situation, we're going to try to make something as big as possible, maximize it, or as small as possible, so minimize it. So, here are the 5 general steps that we're going to take to solve these optimization problems. The first is going to usually be kind of a tricky one. It's a non-calculus step. It's just a matter of applying context, mathematical context, to the real world context. So we're going to set up a model. So we're going to declare variables. We're going to determine what kind of values those variables can have. We might draw a picture if that's appropriate. So basically, we're just trying to understand the question, the situation, and set up a model that's going to allow us to solve the problem. Once we do that, we're going to write a function for what we're trying to optimize. So, for example, if we're trying to maximize profit, we're going to write an equation that is profit equals something in terms of other variables. A lot of times, what's going to happen, and you can imagine this in real life situations, we're going to have multiple variables going into these equations. So the profit is going to depend on lots of things: how many units we sell, how much it costs to produce each one, how much it costs to package each one, stuff like that. We're not going to get into too complex of problems with this, but the quantity that we're trying to maximize or minimize is going to depend on different things. So in this second step, we're going to have to write that equation in terms of one variable. So the profit is going to depend on one thing, or the area of the rectangle is going to depend on one thing. Once we've got that, then essentially what we have from step 2 is an equation, and we want to find a global maximum or global minimum. So at that point, now we're going to start applying calculus. So we will often use the candidates test. It depends on the situation, but we want to figure out where we could have those extreme values, so where we could have a maximum or minimum. That's going to be critical values. So remember, critical values where the derivative equals 0 or the derivative is undefined. If there are endpoints, so if there are limits to how big or how small the variable in the question could be, those are also going to be candidates for extreme values. Then we're going to choose the value that gives the optimized quantity, the number of units that we want to produce and sell to maximize our profit. We're going to look at the domain from step 1 and make sure that we're within that domain. We want to make sure that when we choose that value, we actually answer the question. So the question might ask, how many units should we produce? Or the question might ask, what is the profit? So we want to make sure that we're answering the question with appropriate units. We also want to support our answer using calculus. So we want to make sure that we're using things like the first derivative test or the candidates test to justify that the value that we have is a maximum or is a minimum. What we're looking for here with these optimization problems will be global extrema. So we're looking for an absolute maximum or an absolute minimum. So usually we want to use the candidates test. Unfortunately, a lot of the situations we're going to deal with are going to be open intervals. So in those situations, we're also going to apply that special case of the first derivative test where there's only one sign change on the derivative. So if the derivative is always positive and then always negative, then we know at that point where it changes from positive to negative is not only a local maximum, but it's also a global maximum. So the trickiest part on a lot of these problems is the pre-calculus stuff. It's the setting up of the problem. The calculus part is generally a little bit easier. We're usually applying either the candidates test or the first derivative test to a model once we have a model set up.